Prove by induction that 2 to the power of n is greater than or equal to n squared, where n is a natural number and n must be greater than or equal to 4. Of course, when we're talking about proof by induction, n is always a natural number. Now the base case here will be n equals 4, not n equals 1, as you saw in other examples. We're given that this statement is true for n greater than or equal to 4, so we have to start with n equals 4 and see if it's true. So let's look at the left hand side when n is 4. Well, we have 2 to the power of 4, which is 16. If we look at the right hand side when n is 4, we have 4 squared, which is 16. You can see that 2 to the power of 4 is indeed greater than or equal to 4 squared. As a matter of fact, 2 to the power of 4 is equal to 4 squared. In step 2 of proof by induction, we assume that the statement is true for some value n equals k, where k is greater than or equal to 4. In other words, we assume that 2 to the power of k is greater than or equal to k squared for some integer k greater than or equal to 4. In step 3 of proof by induction, we say that under the assumption that 2 to the power of k is greater than or equal to k squared for some k greater than or equal to 4, that was just step 2, we want to prove the statement is true for n equals k plus 1. So we want to prove that 2 to the power of n is greater than or equal to n squared for n equals k plus 1. We just plug k plus 1 in for n. So this is what we get. So this is what we're trying to prove. So we're trying to prove this thing is true, assuming that this thing here is true. This statement here is true. So we start with our assumption statement and multiply both sides by 2. So if we multiply the left hand side by 2, we get 2 to the power of k plus 1. We have 2 to the power of 1 by 2 to the k, we just add the powers, and multiplying the right hand side by 2 just gives us 2k squared. So we're multiplying both sides by a positive number, so the inequality remains greater than or equal to. It doesn't change direction. Now the reason we did that is because the left hand side of what we're trying to prove is 2 to the power of k plus 1. So if we can prove that 2k squared is greater than or equal to the right hand side of this, k plus 1 squared, then we're done. Because if 2k squared is greater than or equal to k plus 1 squared, if this is true under our assumption, then 2 to the power of k plus 1 is automatically greater than or equal to k plus 1 squared, because 2 to the k plus 1 is, under the assumption, greater than or equal to 2k squared. So we just need to look at this here, this highlighted inequality. So we want to see if it's true. So let's just expand it out and deduce some consequences and see if we get something that's clearly true, which means that this thing must be true. What we do is we square out the right hand side of it, and we get on the right hand side k squared plus 2k plus 1. Now with any inequality, with most inequalities, you try to get 0 on one side. So if we bring everything over, we get k squared minus 2k minus 1 greater than or equal to 0. Often you try to look at this thing and see if it's a perfect square. And if it's a perfect square, then it's definitely greater than or equal to 0 for all values of k, actually. But actually, this is not a perfect square. Okay, the factors of it are not equal. So here's the graph of y equals k squared minus 2k minus 1. Now to draw this graph, I had to get the roots of the equation k squared minus 2k minus 1 equals 0. So that's familiar stuff. You just write down a, b, and c. A is the coefficient of k squared, which is 1. B is the coefficient of k, which is minus 2. C is the constant term. And you plug those into your minus b formula, and you will get out your two roots, which are minus 0.41 and plus 2.41. We can then draw the graph of this. We see that the coefficient of the squared term is positive, so it's an upright parabola. It crosses the k-axis at the two roots. We're interested in the values of k that make y greater than or equal to 0. Now you can see quite clearly what those values are. You can see that values of k greater than or equal to 2.41 will make y greater than or equal to 0. If we take any value of k here, then the corresponding value of y will be positive or 0. It'll be 0 if k is equal to 2.41. Now we're only interested in values of k that are greater than or equal to 4. Okay, that was what we had to initially prove, to prove that the statement is true for values of k greater than or equal to 4. That's what we have here. So we're only worried about values of k that are greater than or equal to 4. And we're only worried about integer values. So the first integer value that's greater than or equal to 4 is 4. The next one is 5, and so on. And you can clearly see that for these values of k, for all natural numbers greater than or equal to 4, then y will be greater than or equal to 0. You can clearly see it from the graph. You can see that the graph is above the k-axis for these values, for all natural numbers greater than or equal to 4. So that's one way to show it. That's one way to show that this inequality is true for k greater than or equal to 4. You can then just reverse all the steps, and you end up proving that 2k squared is greater than or equal to k plus 1 squared for k greater than or equal to 4, which in turn means that 2 to the power of k plus 1 is greater than or equal to k plus 1 squared for k greater than or equal to 4, which means that you've proven the statement for n equals k plus 1, assuming that the statement is true for n equals k. So therefore you're done. Another way that you could prove this inequality for values of k greater than or equal to 4 is to write it in the following form. Basically what I did here was take the coefficient of k and half it. Half of minus 2 is minus 1. Now, if you square out k minus 1, you will get k squared minus 2k plus 1. So you need to subtract 2 if you're going to get k squared minus 2k minus 1. This procedure is known as completing the square. See, now we can write our inequality as k minus 1 squared, in other words, something squared greater than or equal to 2. And you can see that this is clearly true for values of k that are greater than or equal to 4. All you do is just plug them in. Start with k equals 4, plug it in here. You get 4 minus 1, which is 3. 3 squared is 9. 9 is greater than 2. If you put in k equals 5, you'll get a value that's even greater still. You get 4 squared, which is 16. And for k equals 6, and so on. So this is clearly true so this inequality is clearly true when it's written in this form. Use induction to prove that 8 is a factor of 7 to the power of 2n plus 1 for any positive integer n. Now, in an earlier video I covered divisibility examples, proving that some number is a factor of something, or proving that some expression is divisible by a number. It's the same idea here. We could rephrase this as using induction to prove that 7 to the power of 2n plus 1 is divisible by 8. That means that when we divide it by 8, we get no remainder. So we have this expression here, which is going to be an integer. Okay, for different integers n, 7 to the power of 2n plus 1 is going to be some integer, and we want to show that it's an integer multiple of 8, or that it's divisible by 8, or 8 is a factor. So in step 1 of proof by induction, we look at the base case, which is n equals 1. We want to see if 8 is a factor of this thing when n is 1, so we plug 1 in for n. If we plug 1 in for n here, we get 7 to the power of 2 times 1 plus 1. That's 7 to the power of 3 plus 1. So that's 343 plus 1, which is 344. If we take 344 and divide it by 8, we get 8 4s are 32 and 2 over 3 8s are 24. We get no remainder. We get an integer. We get 43. So that proves that 8 is a factor of 7 to the power of 2n plus 1 when n is equal to 1. In step 2, we assume that our statement is true for n equals k, where k is some positive integer greater than or equal to 1. So we just replace n with k. In step 3, we want to use our assumption to prove that the statement is true for n equals k plus 1. That is, we want to prove that 8 is a factor of our expression here with n replaced by k plus 1. So if you replace n with k plus 1, the power becomes 2k plus 2 plus 1, or 2k plus 3. So let's build on this assumption. 8 is a factor of this expression here. That means that 8 multiplied by some positive integer will give us this expression. So m is some natural number or positive integer. We can rearrange this to make 7 to the power of 2k plus 1 the subject. The reason we do that is because now we can go over to this expression here. We see that 7 to the power of 2k plus 1 is part of it. We can actually factorize this term here into 7 to the power of 2k plus 1 times 7 to the power of 2, and then we just add on the 1 here. We can write it like this. If we add the powers, 2k plus 1 plus 2 gives us back 2k plus 3. We can then go and sub in 8m minus 1 for this here, times 7 squared, which is 49, and add 1. Now we want to see if this is divisible by 8. Well, if we multiply 49 into this, we get 49 times 8m. I'll leave it like that. We don't actually have to work it out. 49 times minus 1 is minus 49, and then we have plus 1. Now minus 49 plus 1 is minus 48. Now look at this expression here. We see that this first term is clearly divisible by 8 because it's a multiple of 8. It's an integer multiple of 8. 49m is an integer. So an integer times 8 is an integer multiple of 8. This here is a multiple of 8 because 8 sixes are 48. So if we were to divide this by 8, we would get no remainder. This thing can be divided by 8 with no remainder, and this would be divided by 8. So we'll end up with some integer here minus some other integer. So we'll end up with an integer when we divide this expression by 8. So if 8 is a factor of this expression here, then 8 will be a factor of this expression here. So if our statement is true for n equals k, then it will be true for n equals k plus 1. So in particular, if it's true for n equals 1, then it will be true for n equals 2. We know it's true for n equals 1. We showed that at the start. So that means it's true for n equals 1 plus 1, which is 2. And if it's true for n equals 2, it's true for n equals 3, and so on. So our statement is true for all values of n. Use induction to prove that 2 plus 2 times 3 plus 2 times 3 squared, etc., as far as 2 times 3 to the power of n minus 1 equals 3 to the power of n minus 1, where n is a positive integer. So if n is a positive integer, that means the base case is n equals 1. Now I've written out this series here again. I've written out the first term, which is 2, as 2 times 3 to the power of 0, just to show the pattern that these terms have. So, well, 2 by 3 to the power of 0 is just 2, of course. You can see that the power is 1 less than the subscript. So this term here is t2. Power is 1, it's 1 less than 2, and so on. The next term is t3, and this term here is actually tn, the nth term. So there are n terms in this series. And that sum is given by 3 to the power of n minus 1. Well, we have to prove it's given by 3 to the power of n minus 1. So, step 1 in proof by induction is to look at the sum of this series for n equals 1. Well, the sum of the first n terms for n equals 1 is just the first term. So the sum of just the first term is just, well, it's just 2. The right hand side for n equals 1 is going to be 3 to the power of 1 minus 1. That's 3 minus 1, which is 2. So you can see the left hand side equals the right hand side for n equals 1. So we've proven that the statement is true for n equals 1. In step 2 of proof by induction, we assume that the statement is true for n equals k, where k is any positive integer greater than or equal to 1. So that means that if we take the sum of the first k terms of our series, we will get 3 to the power of k minus 1. So we just replace n with k. So I've written out the first k terms. In step 3 of proof by induction, we have to prove that the statement is true for n equals k plus 1, given that the statement is true for n equals k, given this here. So I've written out the statement for n equals k plus 1. So for n equals k plus 1, we have to get the sum of the first k plus 1 terms. This is the first term, this is the second term, this here is the kth term, and this here is the k plus first term. To get the k plus first term, you just replace n with k plus 1. So we get 2 times 3 to the power of k plus 1 minus 1. So we get 2 times 3 to the power of k. And we look at the right hand side and replace n with k plus 1. So we're summing the first k plus 1 terms when we look at the situation when n equals k plus 1. So we have this extra term basically added on to the left hand side of our assumption statement. So the way we prove this thing here that I've written down in blue is to start off with this here and add this term onto both sides. So then the left hand side of our assumption statement will be the same as the left hand side of the statement we're trying to prove. So this type of problem was covered a few videos back. I did a few series examples. So basically it's the same method here. So here is the assumption statement written down again, and all I've done is add 2 times 3 to the power of k onto both sides. So I haven't changed anything. I'm adding the same thing onto both sides. I'm adding this onto both sides of this here, this statement here. Now you can see that the left hand side will equal the left hand side of what we're trying to prove. So it remains to show that the right hand sides are the same. So we need to show that all of this here equals this here, and then we're done. Now let's look at this here. We can factorize 3 to the power of k plus 1 as 3 to the power of 1 times 3 to the power of k. Now why do we do that? Well, the reason we do that is because 3 to the power of k appears in this here. We're trying to show that these are equal. And 3 to the power of k appears here, so that's what I've done here. I factorized out 3 to the power of k. Now let's look at this here. We have 3 to the power of k. Well, we have one 3 to the power of k if you like. There's one of them here, but we have 2 of them here. Plus 2 of them. 2 multiplied by 3 to the power of k. Well, that we can just write it as 2 dot 3 to the power of k, and then we have a minus 1. So we have one of these plus 2 of them. How many is that altogether? That's 3 of them. Okay, it's like adding 1x plus 2x gives 3x. Same idea. But that's exactly what we have here. So now we've shown that this expression here equals this expression here. So we've shown that if the statement is true for n equals k, in other words, if this is true, then we've shown that the statement is true for n equals k plus 1. So we've proven this statement here, which is got by replacing n with k plus 1. And, well, we're taking the sum of the first k plus 1 terms. So we've proven that this series, the sum of this series, gives 3 to the power of n minus 1, where n is any positive integer.